Because last week when I made my announcement, I said, you could throw tomatoes at me, knowing that Ray would be in the audience. I brought the teacher a tomato. Oh! Well, I understand that you had a lecture from Roderick Tomolka, or I even saw him here last week. And of course, you probably have caught on by now that his point of view about quantum states is the diametric opposite of mine. So, I mean, as a quick cartoon, I would say that that the Bohmian view is that the wave function and particle positions are real, and that all of the complexity of life and tables and trees and people and love and hate and so forth are all very high-level illusions of some variety. That it's a kind of reductionist picture of the world. The world is a wave function plus particles and particle positions, and everything emerges from that. This point of view is the opposite in this way, that the wave function, as the last slide tried to declare, is not real. And I take this very seriously. It's not real at all. Zip, zilch, nothing left to it. But that the variety we see around us, like tables and chairs and rocks and trees and Ray LaFlamme, are all very real things. So real that they're actual components of the world with a kind of depth that even simple particles at the LHC hold. That the world is made of all this stuff that we see around us. So if one takes that point of view, and it's an old kind of point of view, it's called empiricist sometimes, that the world is just everything that we see around us in all its great variety and fullness. If one takes that point of view seriously, then one has to ask, what is quantum mechanics in light of that? What is this theory called quantum mechanics doing for us? Why don't we just say, well, the world just is, here it is, and stop at that? So this quantum Bayesian point of view that Carlton Caves and Rudiger Schock and Howard Barnum to some extent, and Asher Perez, and a little bit of contribution from David Merman and some other people and lots of enemies, is an attempt to address that. So I asked you guys to send me questions, and I thought, well, I gave you the paper, and I said, here's my email address. Please send me questions, and I'll try to address your questions individually. Well, I got some questions. One of them was one of my own master's student. He sent me 3. And here's another one. This one's a good one. This is Cosmin Udadek. But beyond that, I got no questions, even from my 2 PhD students out in the audience. So here's what I think I'm going to do. Just to get things flowing, I'm going to pick up on an old talk that says some things about the point of view. I would encourage you to really ask questions now, and I mean, as things arise. And I don't care how far I get. I don't care if I don't get past the first. No. I don't care if I get past the 5th or 6th transparency. Do they get bonus points if they throw the tomato? Okay, so here's what I think I'm going to do. I'm going to walk down an old talk. Those of you who've seen me talk before will have surely seen all of these transparencies, but you may not have had a chance to respond to them. And let's see how lively we can make this. So, yes?
You want it now or a little later? It's about non-locality.
Oh, I do want that one. But no, but I want to touch it later. How about that? When we get closer to having some terms in front of us. Okay, so my starting point is two tenets.
Can I ask before him?
Just phrase he has this question.
This guy wants some points. We'll definitely talk about non-locality and locality. But I want to start with two tenets. You see, I've been called a solipsist before. So I always have to make it clear in my talks that here's something I subscribe to. A quote by Martin Gardner in a paper titled, "Why I Am Not a Solipsist." The hypothesis that there is an external world not dependent on human minds, made of something, is so obviously useful and so strongly confirmed by experience down through the ages that we can say without exaggerating that it is better confirmed than any other empirical hypothesis. So just as I was telling you before, I believe that this table is here. I believe there's something outside of each individual agent, each individual observer. On the other hand, the point of view that I take of probability is something along the lines of what Robin Bloom-Cahout tried to express to you guys. Maybe I take it one step a little further, but it's along the same lines. It's the Bayesian view of probability, or sometimes called radical Bayesian point of view of probability, or sometimes personalist Bayesian probability. The idea there is that probability theory is a single user theory. It's something, it's a mathematics like logic, that each individual thinker can use. Logic is for thinkers to use. It's not just something sitting out there grinding away the gears and pinions of the world. It's a handbook. Similarly, of probability theory. The Bayesian subjectivist or coherent paradigm is egocentric. It is a tale of one person contemplating the world and not wishing to be stupid, technically incoherent. I'll tell you about incoherence in a little bit. He realizes that to do this, his statements of uncertainties must be probabilistic. What that means is that one uses real numbers to satisfy to express one's degrees of belief and one's gambling commitments, and these numbers should satisfy the axioms of probability theory. So the quantum Bayesian point of view is about taking those two ideas and putting them together. One, that there is a real world out there, and two, that probability theory, whenever it's used, is something about a single user, a single agent making gambles in the world. So from this point of view, quantum mechanics, or at least the formal structure of it, is something that's about the world, some aspect of the world. But because it is written in probabilistic terms, it should be thought of as an addition to probability theory. So probability theory is first. Quantum mechanics gives some extra statements that you add to probability theory. This contrasts to a point of view that you're going to hear from Alex Wiltz whenever Alex talks, of probability theory as something contained within a larger theoretical structure. Quantum probability theory. Oh, they've already had those. Ah, okay. So this point of view contrasts with this. Provisionally so, at least. It's hard to say, because Howard Barnum is now calling himself a quantum Bayesian. So anyway, this is my understanding of what most of the convex operational guys are talking about. They think of classical probability theory as being a subset of something larger. And I think, didn't you have a graph in one of your lectures showing something like that? Maybe you didn't. Maybe you didn't. Anyway, I just want to emphasize a contrast. I'm not talking about this. I'm instead talking about this. Probability theory comes first, and then to it you add extra structure. And the extra structure, extra restrictions, are quantum mechanics. Okay, we're almost to the point where we can address your question. Are you sure you wanted to say it first, or did you steal it from him?
Well, no, I was thinking about it for a little time, so I was hoping to ask it while you were here.
Okay, so here's the point of view. There's when we conceptualize what a quantum measurement is, By the way, I'm giving a talk tomorrow. And for the first time in 5 years, this transparency will not appear in that talk. So if you've seen me before, you've surely seen this transparency. If you haven't seen me before, be thankful you got an opportunity to see it today. I got 2 new ones. One of them taking the place of this one. So when we conceptualize measurement, I'd say measurement is about this. Measurement is about taking the world as a whole, and splitting it into 2 conceptual pieces, one of which I draw as a stick figure. And I call it the agent. Agent is a guy with an eyeball. That's an eyeball. And mustache doing what?
Decommissioning the slide. Half an hour for the whole
You know, I've never seen it that way. But, you know, being a North American, I was taught that when you look up at the moon, you see a man in the moon. So, you know, all my life until I was 32, I'd look up at the moon and I'd see a man in the moon. And then I went to Japan once, and this guy I was with said something about the rabbit in the moon. I said, what's the rabbit in the moon? He was telling me the tale of why rabbits jump. They try to get home. And I said, rabbit in the moon? He said, well, look. And I looked, and I saw the rabbit in the moon. And I haven't been able to ignore it since then. I think I will safely be able to ignore chewing candy, though. This is an eyeball. And what this picture depicts is that we've broken the world into 2 pieces, one called the observer or the agent, and the other piece represents the external world. I put these little mittens on the hand. This is a picture somewhat stolen from John Wheeler. These aren't mitts. You should think of these as measuring devices. So the point here is that a measurement is not a passive interaction with the system. Rather, the measurement devices aren't on the eye, but they're on the hands. When you perform a quantum measurement, you take an action on a system, much like sending whatever you do in the lab. So there's the agent, there's the system. A measurement is an action that one takes upon the system. And in consequence of the action, the system acts kind of as a catalyst. It creates something. This interaction creates something. You call it an outcome. And the agent becomes aware of the outcome. He has an experience. There's a consequence to his action. In the formal apparatus of quantum mechanics, actions are represented by positive operator valued measures. And the experience that the agent receives is represented by one element of this set. The system is described by some Hilbert space. And I usually think of Hilbert spaces as finite dimensional, and that'll be somebody's question out there. I think Matthew's question. We'll talk about it later. And I put the quantum state up next to the head of the agent because I want to be absolutely clear that this object doesn't live on that. Rather, it lives in here. It's the agent's degrees of belief about the consequences of his actions upon a system. So that's the picture of an agent in a single system. Here's the picture of an agent in 2 systems. Pretty good, huh? The agent, if he thinks he has 2 systems, can take actions on each of them. And what does it mean for there to be 2 systems rather than 1? It means that taking an action on one system has no causal effect on the other system. Yeah, that's it. So what do you call that? I would call it local realism. But since I'm not talking about hidden variables here, I don't know, maybe you wouldn't want to call it local realism. That was one of the questions. So I've now addressed one question. There's something external to the agent. He can take actions on them one at a time. And if they're not in contact, the assumption is that taking an action on one doesn't immediately affect the other. Now, one of the points of this paper, how many people read more than 3 pages? Really? How many read more than 5? Same number. How many people got to the Bell? How many people got to the Bell's theorem discussion? Oh, a lot less. Okay. Okay. All right. So what's the point? The point of the Bell theorem, the way I express it in the paper, is that sometimes it's presented as showing a fallacy or an inconsistency in the idea that there are really two systems there. Because one, for instance, can consider an entangled state between these two systems, and an agent can now interact with one of them. And he interacts with one of them, he gets an outcome. Well, then he can go to the next one, and before he ever interacts with it, before he touches it, he says, with probability 1, I say such and such will occur, based on what he had seen previously. What is one to draw from that? What conclusion is one to draw from that? Well, the usual Bell-style argument, and I'm not at all being rigorous here, because I want to do some more stuff before any attempt at a little rigor. But the usual Bell-style argument goes that he couldn't have known what outcome he would get at the second object if it didn't already have a value sitting there waiting for him. Therefore, there must be a hidden variable theory. Then Bell goes on to prove that any local hidden variable theory would be inconsistent with quantum mechanics. At that point, he backs off on something. He backs off on the idea that these things are causally disconnected and says, aha, the world is non-local. The quantum Bayesian of the style of Caves and Schoch and Fuchs and Appleby instead says, no, we don't back off on that idea. It would be hard to imagine what science would be if the world had all these tendons running between every 2 objects and every 3 objects and every 4 objects. So we back off on the idea that there was something sitting there. Probability 1 statement doesn't mean that. But let me go further down before we get into that. But I will take your question, because you've been waiting on it. Uh-huh.
Okay, so I was actually about how we violate probability quantification. So my question is, so same that you said, if you describe that measurements are almost creation, in the sense that when I measure, say, a spin-up particle, and I see spin-up that in the sense that's been created, now exists, still not exists, but exists to me, real. And then I could say, if I know prior that I created a bipartite system that was entangled, and I measure spin-up on one subset system, then I could say that if I would go over and measure the other system, I would obtain spin-up as well, right? So in that sense, there's no probability because I'm actually going over doing the measurement. But so then my question is, if to violate Bell inequality, it seems to me that another observer who also knew that the system was entangled initially, so to measure the second system after I measure the first system, then in their moment of creation, their measurement will produce a result also producing out and violate Bell inequality, like we know quantum mechanics does experimentally. So then, I guess my question is that there are 2 moments of creation that are independent of one another, but producing results that are correlated. My question was, how is that different from non-locality in the traditional sense? My thought was that because we don't assign a hidden variable to the state of the system, then there's no, besides the information transfer, there's no reality to the system independent of our observations. So there's no concept of locality in that sense that when the measurements occur, just because there's nothing going on between them. And I guess what I'm saying is this kind of creation non-locality distinct enough from just the non-locality of a hidden variable method beyond just no signaling? And
Is it distinct enough?
to call it local, call that process locality. So this seems what you're agreeing.
The danger of getting questions is because they can have a whole lot in them. And yours had a whole lot in it. And I'm not quite exactly sure how I want to address it. Let's think about one thing that we might want to call non-locality, and we might not. Don't know. This is a kind of picture that I think Rob Speckens is attracted to. Did he lecture to you guys? Okay. We could imagine that this thing called an outcome is a joint property of both things together. So for instance, we might imagine that in this block, there's a hidden value 0, 1. Okay? And in this agent, even though I've drawn his belly really thin, maybe he's got something in his belly that's a value 0 or 1. And this thing that we're calling a measurement, we used to think of just reading off the value of something in there. Instead, maybe it's doing this. It's checking the relation between the thing that's sitting in there and the thing that's sitting in his belly. So for instance, maybe the measurement reveals the parity of the two things. The hidden variable in his belly is forever hidden. The hidden variable in the box is forever hidden. But the relation between the two is something that can be experienced. Okay? So if you take that picture seriously, then you might well want to call this a kind of non-locality. Because what happens when this guy interacts with this system is it reveals the parity of the two hidden bits that can never be unlocked. We'll never see them. In fact, John Smolin might, well, you don't know John Smolin, but he would say, why don't you make a many worlds picture of everything? But anyway, this thing called measurement reveals the relation between these two things. Consequently, it reveals the relation between these two things. And you might want to say, that's a non-local theory. So a relationalistic theory is a non-local theory in some sense, because there's no one thing over here. If you walked up to this and somehow magically opened up the box and looked in, seeing the value of the hidden variable would reveal nothing whatsoever about what would happen when this guy interacts with it. Knowing that alone doesn't do it. So the property is non-local in that sense. It's spread over all space between these two objects. Quantum Bayesianism has a bit of that. But I don't quite like the picture of things sitting in the bellies of the agents, hidden variables in the agent. I don't think it's a productive picture. So I sort of walk around it.
I guess to follow up, so anything that for the two observers I was suggesting, the property of the fact that they know the system is entangled is what allows them to see Bell correlations, or by the violation of Bell's inequalities. And in other words, if one observer was unaware that the system was entangled, and the other one was, and the one who was unaware performed the second measurement, it's impossible that measurement may or may not necessarily violate Bell's inequality.
The way you're stating things sort of falls out of the framework of the way I would talk. So it's hard to address. So for instance, when we've got two agents, you're sort of using, if I understand you correctly, you're using language that says, here's the one agent, here's the system, here's another system, and this agent says EPR. So what he's talking about are these two systems, okay? And now you've got another agent, and you were saying things like, oh, he doesn't know.
Yeah, actually, I was going to say, it makes no sense to your point, because it doesn't matter the fact that the results have to be coherent between observers, that's all that matters, right?
Well, in this point of view so far, as expressed, they only have to be coherent for the one agent.
Okay.
In that sense, it's a single user theory. Now, if I'm an agent and he's an agent, and there's evidence that he is, when we talk to each other, then you might just say, that's one agent. Two communicating beings. Well, there's a lovely quote from my favorite philosopher that I like that says, what is the self? Well, the self taken in I take self in the largest sense possible. The self of a man is his wallet and his wife and his yacht and his house and his friends. So similarly here, just as you talk about isolated systems, you say, I'm going to think of this piece of the world as isolated. Then I'd say if you took two communicating beings, like Joseph and myself, then you might just consider us an isolated agent, one single agent. If we're talking to each other, I don't see much distinction between the two minds. The subject matter of probability theory, though, is a single agent, whatever that means.
That's my uncertainty. I think, okay.
Is this going the way you guys are okay with it?
This is great.
It's not too slow?
No, it's up to the students, right?
The students are in charge.
Okay. Now, here's the way I make fun of people who call me solipsist. I say, look at my diagram. It's not that. Rather, it's this. That quantum theory is a single user theory, but just because it's a single user theory doesn't mean that there's one user. It means that I use quantum theory to make sure that my gambles and decisions are consistent, and you use quantum theory to make sure your gambles and decisions are consistent. And we all can use quantum theory. Hooray, it's a nice thing. Okay, what do we learn from this exercise, though? I think that despite all of this egocentric sounding stuff, that quantum theory is a single user theory or should be construed as a single user theory, not as a statement of what reality is in itself. So I do very vigorously declare that quantum theory is not a picture of what reality is in itself. It doesn't mean that we get no new knowledge about the world from quantum theory. We have learned something in making the transition from 1895 to 1902. We've learned something in making the transition from 1902 to 1927 when quantum theory was firmly in place. The thing that we've learned is that we don't just use probability theory, the full big slab that I showed you earlier, but we use some kind of restriction of it. And that restriction is encoded in the calculus of quantum states and positive operator valued measures. As soon as one recognizes that, one can ask the question, why are we using quantum states? Why are we not using some other structure? For instance, something of the structure that Howard Barnum was talking about if he talked about convex operational theories. There, the setting is a convex set, general convex sets with certain properties. Within that whole framework of theories, quantum theory is just one of those. So one can ask the question, why are we using this particular one within the framework, not another? And to the extent that one can answer that, to the extent that one can compare the calculus of quantum mechanics to other possible calculuses, then one is learning something implicitly about the character of the world. So before 1927, we thought the world was made of solid stuff that bounced off of each other, obeyed field equations and so forth. And after 1927, we started to realize, that's not a good picture of what the world's made of. We learned something about what the world is made of from the character of the theory. So taking the egocentric point of view, or at least this is what I want to stress, taking the egocentric view about quantum states doesn't say that we're not learning anything at all about the world. On the contrary, I think we're learning a lot, and it's just a question of what we're learning. What's the ultimate goal of the research program? I'd say it's this. It is to recognize that quantum states are statements about agents, and we as physicists would really like to say something about the world as it is without agents. Well, if quantum states say something about an agent, what we're really striving for is some statement of what quantum mechanics is telling us about the world that makes use of no quantum states whatsoever. So when we come to an understanding of what quantum mechanics is telling us, it had better be a statement that doesn't involve psi. You see how different this is from the Bohmian point of view, because they would say what quantum mechanics is telling us about the world is that there is a psi. The world possesses it. It's a property. It's like a field value. Yeah?
So it's not clear that we can do this, right? Like, quantum theory is telling us how we, as we interact with the world, how we acquire information, how we control things, control, et cetera, et cetera. So if that is, I mean, it's not clear to me why we should look to be able to say anything more than that. I mean, we can say there is objective reality outside of us, but the only way we can ever get any or know anything about that reality is in the way that we poke it and kick it from. And that's what quantum theory tells us exactly. So why do you have a hope of it?
Well, I have a hope of that. It's for the same reason that I really, really, really get hurt when people call me a solipsist. And I really, really get hurt when people call me a positivist or when they call me an instrumentalist. Is because I hold out the hope that actually it's useful to posit things of the world. So it's true that we can't get any, I mean, you know, how did you put it? You put it nicely. We can't get any, did you say that? Oh, the physics should be about our bumps and kicks to the world and perhaps nothing more. And to that I would just say, well, you know, sometimes it's useful to make up a story about what's going on without kicking it. I'm not against that. Just seems that quantum mechanics has tried to stop us from doing that in the naive ways. But, you know, I find it useful to think that when I'm not watching her, my wife will go to the thrift store and shop for junk. Because I've seen her do it so many times. And if I'm working under the assumption that she'll buy some junk today from a thrift store, then I won't be so surprised when I get home and find the junk that she's bought. So, you know, you make up stories to try to alleviate uncertainty, or you make up stories about the world so that you gain a little bit of predictability. And those stories are often about what the world is doing without you before you bump into it. And I don't think there's anything wrong with doing that. The only claim here is that our ultimate story, A, is not going to involve hidden variables as usually construed, and B, it's not going to involve this thing called a quantum state. That's the only claim here. There were, which of you was first? Be honest. Well, you could see him, but he can't see you. So you're probably first.
You want hidden variables, but how does a statement about the objective character of the quantum world differ from some kind of hidden variable theory? What can you imagine that would fall under that category but would not be ultimately hidden variable?
I see. You didn't get to page 19, did you? What I mean by that is that if you take this empiricist point of view about things, you know, that the world is made of tables and people and detection events at the LHC and DNA and everything that you can name. If you take this point of view, then you have to ask, well, what is physics in the light of that? So if you take a non-reductionist point of view of the world, so in other words, of you, I wouldn't say, oh, you're just a big pile of carbon and oxygen and, you know, some other constituents. You're more than that. Just as I would say that of you, of a little measly carbon atom, I wouldn't say, oh, he's not much. You know, maybe there's a whole world there. Sounds spooky. Hang on, though. In other words, whereas I wouldn't want to reduce you to a pile of carbon, I wouldn't want to reduce a pile of carbon to you either. So one has to ask, well, what is physics in the light of that sort of picture of the world? And starting around page 19, I claim that what physics is about is trying to identify as many things as common to as many pieces of the world. So for instance, of all of you in the audience, I know that you have something in common that I'll call carbon. So I want to take away the picture that you're made of carbon and put in its place that, well, you are what you are, and Joseph is what he is, and Juan out there is what he is, but all three of you have certain characteristics in common. And what physics is about is identifying those characteristics that can be applied to as many things as possible. From this point of view, Newton's theory of gravitation is about as good as you can get. In other words, he didn't say that the world is nothing but masses. Instead, he said, oh, of every two things in the world, they attract each other. And they attract each other dependent upon some number intrinsic to this one and some number intrinsic to that one. Every piece of the world has this in common with every other piece of the world. Oh, and then I make a smart remark in the paper about, I made a lot of them. And two insults, very intentionally. So if you find the insults, you get bonus points from me. Yeah, so I make some remark about, would Newton be respected in this day and age when all the newspapers say that what a physicist is about is trying to find a theory of everything? Well, by these lights, Newton was an awful physicist. He didn't even come close to a theory of everything. But we all know that's bullshit. He was a great physicist. And the reason he was a great physicist is because he found a theory of one aspect of everything. And there's no one else in this building that has done that, found one aspect of everything. So, in place of hidden variables, this is a long way of answering you. I think that quantum mechanics, with hindsight now, and after 60 years of foundational struggles, I think it certainly makes me take more seriously the idea that quantum mechanics is no theory of everything. It can't be. But that it is identifying one aspect of everything that had been previously unnoticed. And that aspect of everything, I don't know what good name it should have, but we'll call it Hilbert space, provisionally. So of every piece of the world, this is why I thank Seth Lloyd. I can't believe I thanked him. He pulled off a shoe one day in a lecture and said, you know, you can use anything for a quantum computer, like this old shoe. Well, that's true in some sense. And the truth of it, the piece of truth in that, is that before quantum mechanics, a shoe was just a shoe was just a shoe. That's all it was. I mean, it had certain properties to it. But once we learned quantum mechanics, we realized you can do more with a shoe than you had thought previously. So I think that's what quantum mechanics is identifying, some extra way of stroking matter or petting matter that'll make it do some interesting things like factor large numbers. I hope that answered you. There was something else.
So I guess the core of what's left of my question is you've now sort of said, in your view, what we're trying to accomplish with physics is not sort of a reductionism, which is, I guess, the conventional view, but instead you're saying, we're, at least with quantum theory, is we're now adding common aspects to everything, right? But it's not clear to me what the mechanism is to go from our quantum formalism, which would you treat as a purely personal thing, to going out and saying, and okay, now this is a mechanism that my coffee mug has, or like I have now added some property to my coffee mug associated with quantum mechanics, right? Like we have quantum mechanics now. My coffee mug is not the same as it was in 1890 or whatever, right? But it's not clear that quantum formalism, in your view, tells me like what aspect that is beyond like vaguely saying, oh yeah, it should be related to the Hilbert space dimension. Mm-hmm. Right, so what is, like, I guess I'm not even looking for your answer, but what is in your view the program to answer that question? Like, what encompasses the new physics of my coffee mug?
That's the toughest question I'm going to get today, I think, because I don't know. I really don't know. I really, really don't know. I can point out some things that are common. So, for instance, I mean, you just look to all the phenomena in quantum information and quantum computing that we now know. These are things you can do with Hilbert space. We can factor large numbers, presumably exponentially faster than we could have if we had matter in its, if we just treated matter in the way that we had always treated it before. We can build secret keys into systems by preparing them correctly and sending them on their way. We can solve certain communication complexity problems exponentially, with exponentially fewer resources than we could before. All of these things, I can say, aha, you can use Hilbert space for this, and I thank my lucky stars that I learned, I had Nielsen and Chuang's book to teach me these things. It would be nicer to say something in a way more akin to the way Newton said things. Every two bodies attract each other. And then some clever guy comes up and he says, oh, because these two bodies attract each other, I can build an engine. I can build a heat engine with this. I can build a pulley system. I can do this. I can do this. I can do this. And it's all because of this one underlying statement that has a very simple form. So I can't answer your question. I just think Hilbert space, and the amount of it, is going to be the answer to some very clever idea. That's all I got for you, though. The hidden variablist will say, well, I can tell you that the world is made of hidden variables. And the Bohmian can say, I can tell you that it's made of wave function and positions. And they all have pat stories that, in my opinion, are going to disappear in a few years. So I'd rather stick with I don't know. Shall we go forward? Oh, now the tough one. No, he actually asked the toughest one all day. He can't be beat.
So I'd like to tell you why you should be happy with life. That's the alternative.
Go on.
So basically, I mean, I guess I come with a preconception towards what it means to work with forms. I touched on this earlier in the class, but like we have an operational interpretation of quantum mechanics. So you and I and Raymond and Roderick Tomulka and Bohm, and we can all use quantum mechanics to make predictions. We all understand it correctly from an operational point of view. So the question of interpretation for me goes beyond that. And it's to say, look, we have this set of objects. This set is called the set omega. And it's a set of things that we presume exist. You agreed that that table existed earlier in this lecture. You said there's good evidence that I exist.
It's not exactly the same table right now.
Fair enough. But the point is, we're gonna populate this set with stars and elephants and tables and people.
Talking like David Deutsch.
Yeah, no, I trust that from his stuff. So the idea is.
You didn't say with a British accent.
Yes. I didn't draw it for you. Here's the world that has stars and elephants. This is a QCMC talk about 5 years ago where David Deutsch gave a video conference actually to the conference and treated us like 5-year-olds and Mr. Rogers or something. I got to see him draw reality. Anyhow, so that left a mark on me. You do it. So anyhow, where was I going? Right, so you have this set of objects, and then for me, the question of interpretation, the non-trivial question of interpretation, is constructing some kind of mapping from the formalism of quantum theory onto that set. And to say, okay, well, these objects exist. I'm going to either I'm going to say, okay, well, so the many world people have some, I don't even know what they do for that, but the Bohmians have a way, they say, well, okay, one thing, we need to reformulate quantum mechanics this way, then you can assign a position, that maps onto things we can observe. The wave function is real, but it doesn't map onto things we can observe, so it's a little bit unusual that way. And then of course, the alternative is to say, well, look, the quantum description is incomplete, I don't know what the completion is, and so I don't know how to make that mapping, but what I do know is that quantum states don't map onto these objects. And that's basically Einstein's point of view, as I think it, as well as Valentine and others. So,
Who are you?
me. Rob Speckens, who he's my disciple after all, so I'll take credit for his point of view on that. But lots of people, Bohm, I think, well, maybe not Bohm, but Bell, I think, believed this. And
no, it's not clear to develop.
I don't want to revisit history.
But I got the point. The point is that quantum mechanics is incomplete and a complete description exists.
So basically it's saying, well, there should be such an interpretation, but quantum mechanics, with the formalism as we have it, we can't construct that mapping. And so my issue is this, is that, if I assume that you're saying something that's adding to that discussion, then I take it to be solipsistic. And if I don't take that view, then I don't see what's being added to that. That's my issue. So it's, I guess Gosh, I won't put a word to it, but that's my concern.
Yeah. How about if I say it this way? I think Einstein was spot on, bang on. How do they say it? I think he was. But I think the quantum description is incomplete, it's radically incomplete. Because, you see, the way I view the sort of philosophy going on behind you and Rob and McKenna and I don't know who else to lump you with. I can certainly lump Rob with Daniel Dennett. I don't know about you. Is that, okay, you say, I recognize that quantum mechanics is incomplete. That buys me a little bit of interpretive traction. I get some ways toward understanding quantum mechanics. I get all the way to the level of these toy models. And then there's the hard part, the non-contextuality and all of that. But the faith is that you're going to be able to cross that divide. And the way of crossing the divide will be recognizing quantum mechanics is incomplete. That's why we got as far as the toy models. But then we're going to find another layer underneath there, just a little bit further down. Maybe it's a good distance down, but we're going to find another layer where all of a sudden we can describe the world in one sentence or one equation or one something, some linguistic structure. So when I say it's radically incomplete, I'd say that's not at all the same thing as solipsism. Solipsism, you just look up the definition in the dictionary, and it says that I am the sole reality.
Yeah, no, I agree. So, I mean, if you're
So I'd say, no, I'm not the sole reality, and no single equation is the sole reality either. No single story is the sole reality. Nothing that you can put in a sentence is all of reality. Reality is more than that. So that's why I would say it's along the lines of what Einstein was wanting, but it just takes it to a ridiculous extreme.
So if I'm looking at it, so we're projecting out the final account of what's real, well, there may be no single account of what's real. That makes it straightforward and then you have also have the subjectivity map of everything that's real if you want to like somewhere.
Yeah. I'm banking on the fact that that's not correct. And moreover, I think it's more productive to take the opposing point of view. So for instance, tomorrow's talk is going to be, one of the questions is what's the difference between Valentine's view and the quantum Bayesian view? It was certainly you, but somebody else asked it as well. Was it Matthew? Was it you? No. Oh, it's Cosman. Yeah. At the end of Cosman's, no, it was somewhere in there. Could you comment a little on someone like Leslie Ballantyne's views on the issues from Section 3 and his best argument for his views and how you understand them? I don't know what his best arguments are. This may be a strange request, but I think it's interesting to see how two people with opposing views evaluate and argue against each other's best arguments. I think of it as a kind of second-order evaluation, two positions, with the first order being just looking at both and evaluating them personally. Okay. Well, anyway, so there's Ballantyne, and I think you're right. I think he is representative of your view and Rob's. They're all representative of each other. I mean, here's the only leg I've got to stand on. It's this. If one really takes a personalist Bayesian view of probability, then one finds oneself so incongruous with everyone else around them, talking to them, that you have to work really hard to get a picture and a story that will seem sensible at the end of the day. So, for instance, you know, I can imagine a conversation with you when I met you in '99, and you might say, you know, what is this bullshit about these quantum states being personal? We know that in all of quantum information, we're constantly talking about unknown quantum states. We teleport unknown quantum states. We provide quantum error protection to protect unknown quantum states. and whatever else we do with unknown quantum states. And I was deeply aware of that I shouldn't be talking about unknown quantum states if I didn't believe that they could be out there without being known. So I better have some story to tell in each one of these cases. So particularly, what are the quantum tomographers doing when they're measuring the unknown quantum state? I needed a purely Bayesian account of that. And consistency and wanting to save face in the community then pushed me to try to prove something like the quantum Diffie-Hellman theorem.
But I always just naively interpreted an unknown quantum state as just an unknown probability distribution. You have some process that produces objects with some probabilities, and you can then tomographically determine what that probability distribution is, and it's the same problem in quantum mechanics. So what's the difference between, so taking an epistemic view of quantum states, that's how I interpret the meaning of unknown quantum state. But you have a more subtle problem, I think, is that?
No, I think it's the same thing.
Oh, okay.
It's exactly the same thing. So Diffie-Hellman was spouting off this personalist view of probability, and his
I see.
his opponents were saying, well, what are we doing when we're performing statistical tests? We're finding the probability distribution that's there, that's out there.
Oh, I see. Sorry.
You can't make sense of that with your personalist Bayesian account. Should I stop?
You shouldn't have answered his question.
Make sure that it's.
Okay, so let me quickly answer this one. The point of tomorrow's talk for anyone who's going to come is that taking such a weird stand on quantum states pushes you to try to prove lots of theorems. Now, Professor Ballantyne has certainly done that in the quantum chaos program. There's no doubt about that. But the range of sorts of things that we've had to prove for consistency's sake, I think, is larger in the quantum Bayesian business, because we couldn't just naively say, well, there is an ensemble. I mean, when Ballantyne says ensemble, what does he mean? He never tells us what he means by an ensemble. Is he thinking a hidden variable, that there's a collection of true values for position and momentum there, or is there not? Okay. Fair enough that he doesn't have an answer to that question yet. He can declare, well, I don't really know what I'm talking about. There's just an ensemble.
The problem is the set of systems prepared according to the same preparation procedure. So you might have one sample from that ensemble if you have a single system.
And what does that mean, same preparation procedure?
Well,
So for instance, I pull out a coin and I flip it. No, part of what's at issue is whether it does make sense to say that one has done exactly the same thing twice if it leads to differing outcomes in some later observation. Maybe we'll pick that up again later at another, because Ray said I should be taking other people's.
Language that contradicts your own views, because you want to. You say the task of quantum interpretations is to map these statements about these abstract axioms of quantum mechanics onto some set omega of things that exist. But then, like every time, like last term in quantum theory, you never wanted to talk about rho as a state. You always talked about it as a preparation. So you don't take rho and point to something out there. You understand rho to be a collection of information taken from some procedure that you've done. It seems like with all the, and that's, again, with quantum mechanics as a instruction manual, that's all it talks about. It talks about procedures. It talks about if you do this and you do this, then you'll see this. So you're not, so it seems at the heart of it, you can't do what you want to do. Quantum is telling us, isn't that making sense?
How can we? Yeah. Tell me what you said. I'm sorry. I wasn't talking to Craig. He was listening to the tone of voice. He could only be talking to me in that moment.
please go on.
You were scared and trying to escape.
So what did you get?
I'm emphasizing how to interpret rho as describing a preparation.
Right, right. So it seems that what you want, what you feel an interpretation of quantum mechanics it should be, you can't really get.
Well,
Because
there's,
quantum
I have the
is telling you
operational
that.
interpretation and ontological interpretation. There's like 2 levels of interpretation.
So,
you have to figure out-
okay, well, so okay.
But this is as good a time as any to bring this up, maybe. I'll give you this to work on. Imagine a student, it's connected. Just have patience with me, you'll see it's connected. So imagine a student who's given a homework problem that says something like, you're given a pendulum of a certain length, L, initially at some angle, theta, and with some motion, some momentum, P, so forth. And the student is asked to calculate something about it. And the student stops and says, well, I could calculate that, but that's really not the interesting thing, to find the answer to your question. I want to know, why was this its initial condition? And you say, if you're the professor, you would say, well, that's a stupid question, because professors aren't supposed to do that. But you say, well, it's just the initial condition. There's no call for me explaining the initial condition. And the student says, no, I want to know why it has this initial condition. Okay. This whole Bayesian point of view is that this thing that I'm drawing next to his head is analogous to this. And people, it seems, like the naive student, want to say, well, why that initial condition? Why this quantum state? They insist on this. They want an answer to that. And the operationalist steps in and says, oh, you know why? Because there was a device back here called the preparation device. And they think that that solves something. But I would say all they've done is they've taken it from here and they've put it there. And now I could be the naive student yet again and say, why there? Why that one? It seemed like your question was a little bit of this flavor, that Joseph is being somewhat inconsistent when he...
Just on that, what seems to be the contradiction in terms is that you're saying you want this mapping between objects and objects, or on elements of the formalism of quantum mechanics and real things, but then you talk about the state as a preparation procedure.
Oh, yes, exactly.
Rho is not something you can point to. Rho is something that you tell a student to do in the lab. And
yeah, so you can't drop the adjective like operational versus ontological.
right.
So to do quantum mechanics, you need an operational interpretation. That's something we all agree on, and that's scientific. But then the ontological interpretation is something that's pushing beyond known science. And say, can we say more about reality by interpretation, and what does that tell us about where to look for?
Right. But I don't think one can go about doing that in this case by saying, okay, I'm going to map my POEMs to some real thing. I'm going to map
Well,
my
actually,
to
you
something.
can. I mean, Bohmian mechanics is a perfect example of that. But there exists some. I mean, that was the point I would hope everyone took from Roderick's lecture, was that whereas lots of people thought it was impossible to do that, and Einstein insisted it was possible, Bohm showed that it does exist a way to talk about an objective reality underlies the operational formalism.
But I mean, not to the whole point. I think one would normally mean that, because he's saying that the wave function doesn't live in space-time; it lives in configuration space. So you're still not projecting that onto a set of elements and stars.
No, I agree. The map isn't onto that set omega described, because in the Bohmian case, you get maps onto things outside of that set, right? Things that you don't see in every day.
So, but even in the case of Bohmian mechanics, the domain of your map is not formalism of quantum mechanics. It's these, well, aside from psi, and then these real particles. So the Bohmian is just adding something more than saying, okay, never mind the formalism, they add this kind of, it's like a cheap fix, it seems. They just add it in, and then they say, oh,
Words I would have chosen
now
myself.
this is free. And that's not what you're talking about when you're saying, well, you want to map. Why does physics necessitate the absence of quantum? Like you're not.
You guys are too young to have been here for the conference 2 years ago when there was a panel discussion between Tomoko. Well, it was a panel discussion, and among the panelists were Tomoko and Bill Unruh from Vancouver. And Tomoko said, we have a scientific theory, it can answer some questions that standard quantum mechanics can't answer. For instance, precisely how long a particle is in a potential barrier that it couldn't be in classically. And it's the only interpretation of quantum mechanics that can answer this question. And Unruh said, no, it's not. And Tomoko said, yes, it is. Unruh said, no, it's not. My theory answers it. And Tomoko said, what? And he said, in my theory, every particle is in every barrier, no matter how high and how thick, for exactly 7 seconds. And Tomoko was taken aback. He said, that's not a scientific theory. And Unruh said, it's every bit as scientific as yours. Now, there's a difference. They've got an equation, and Unruh doesn't. And that gives it a kind of sheen, I think. It makes it look scientific. But to the extent that it adds these extra things, actually, they may have pragmatic value. And I mean, here's where I would give the Bohmian his due. So I don't know if you guys know what a pragmatist is, but I'm pretty aligned with this philosophical school, which says if you find something useful, any idea useful, why not adopt it? So the question for me would be, is the idea of Bohmian trajectories useful for doing physics? What I mean by doing physics is not solving the pet problems of your interpretation, but for physics as widely construed by other people. So an example I like to give is an open problem. It had been an open problem in quantum information for years and years, for about 10 years, was suppose you're given a quantum channel. You're given 2 copies of it. So quantum channel takes density operators to new density operators. And a question that had been open forever is, suppose you take 2 copies of the channel, and you ask, what quantum state for A and B should you put in here so that it leads to the minimum entropy output? Which one should you put in there? And the conjecture was that an unentangled state would lead to the minimum. But no one could prove it for years and years. Finally, a counterexample was found that actually for some quantum channels, it's optimal to put an entangled state in, and it'll lead to the minimum entropy. Well, here's where I would say the Bohmian conception would have been a good one. If you take a Copenhagenist and a Bohmian, and you put them in one room, and you say, here's a problem that neither one of you have ever seen before. Use all the imagery you want. Use all the paper that you want. Use all the computing power that you want. But one of you, I presume, is going to work with the Bohmian picture, and the other one is going to work with some picture that doesn't have trajectories. If the Bohmian would have said, you know, by thinking about my trajectories, I got a handle on this problem that nobody else could get and could find the answer faster, then I'd say, let the Bohmian have his trajectories. Nothing wrong with that. They're an aid to thought. So it wouldn't be so bad. So just because something's not observable doesn't mean it's not a useful construct. I mean, there are lots of things that are unobservable, like electromagnetic potentials, but they help you solve problems. It's just with the Bohmian community, I haven't seen that kind of pragmatic value to their picture.
Where Bohmian mechanics is explicitly non-local. The hidden variables, you assign some reality. Granted, we can't verify scientifically if that's the correct one. You see that it's non-local, that there are non-signaling causal influences in the theory. And then Bell asks, well, can we show that any such ascription of reality has to have this property for entangled states? It shows that that is true. So Bohmian mechanics gives the insight that using entangled states, we have some kind of special resource, which I think is lost in this interpretation because you know that there are games you can play where entanglement as a resource helps people answer questions in a more pass some tests they couldn't pass without entanglement. You know, the kind of the computing science way of thinking about entanglement. So I think that for me, at least, and maybe I'm studying the history well, so I'd be happy to hear different points of view, but that for me is an arc where the ontology dreamt up in Bohmian mechanics actually gives us insight into special properties of the theory.
Point taken, but I think you're far too abstract. I'm talking at the level of homework problems and textbooks. Nothing has been more useful than the introduction of electromagnetic potentials.
Yeah.
I mean, they're workaday, you use them all the time. So, yeah, it's true. I can also say, oh, look at the power of many worlds. It led David Deutsch to find one algorithm. And it was an important algorithm, and it got the whole ball rolling. But I don't think you use that as evidence for accepting the many worlds.
I think it did influence finding.
But your argument was that it shouldn't.
Yeah, to some extent, But I'm really hoping for something that really goes all out to the point of, if you think in this manner, you'll go in the laboratory and you'll do amazing things that you couldn't otherwise.
I think I was going to say that based on what Professor Emerson just said about the non-locality of Bohmian mechanics implying it will give you entanglement as a resource. I was thinking that this interpretation of what I understood from when I took my first question, you just replace the idea of non-locality with the idea of coherence of an individual agent, where that agent used to, at some point in time, consists of independent agents. So basically, a super agent of communicating agents that at any point in time talk to one another. Then you get that same, that just to be consistent, for all observations to be consistent, you obtain this kind of non-locality without explicitly calling it that. And you have, again, entanglement as a resource.
How does entanglement fit in with that?
Well, no, I'm just saying, you just use
I think that would be unnatural from this point of view, the idea of a super agent.
Yeah.
But it'd be unnatural from my point of view. So, you know, there's no super agent out there who's looking upon the universe and says, psi universe.
Well, that's not what I meant, though. I just meant that from what I took your answer to my first question to be that the reason we see the Bell dilations is because at some point in time, when the two observers communicate, they are, as you're saying, one agent. So for the results to be coherent for that one agent, they had to have been consistent when we think of them as independent agents. My point was that I think that process of consistency is equivalent to non-locality in the hidden variable sense.
Okay. I would gamble that it's not, but I don't have a reply to you now. If you would write that in email, I'll think about it harder and then try to reply to that one next week. This week. 2 days, thanks. Yeah.
So in my view, the value of the Broglie-Bohm interpretation is sort of that it fails to fail in the sense that if I want to take my naive interpretation of reality, where I have some reality and you have some reality, and there's some sort of like coordinate transform-esque thing that can take my reality to your reality, right? Like just the intuitive view of reality. Right? Then quantum mechanics doesn't take that away from me. I mean, I have an explicit example of a model where I can keep my view of reality, right? And I really like that view of reality, right? So now we go to your model, and you said to Joe, well, your bet is that view of reality doesn't exist, right? So how are you justifying that bet? Like, what in your view makes it a good idea to throw away my naive but very attractive view of reality and take up, the sort of quantum Bayesianism?
What's your fire?
Yeah, that's right. It has everything to do with that, or your disposition. My friend and collaborator, Marcus Appleby, I wish he were here to react to what you just said when you said that your very nice conception of reality. He would, as Osa knows, he would just say, what? It's a dead reality. It's a reality in which nothing happens. And he would go on and on and on and on. So certainly there's a philosophical distinction between certain points of view. I mean, some people feel very comfortable with the idea of a big block universe, a determined universe. And some people feel horribly uncomfortable with it. I'm an example of someone who feels uncomfortable with it. But I got a better reply than that, and that is that I would say, I mean, there was something absolutely beautiful about Rob Specken's toy model. And it was this, that of course he didn't get all of quantum mechanics with the toy model, but qualitatively he got 25 or 30 features from a single principle, and a very simply stated principle, this thing that he called the knowledge balance principle. It's that of his toy bits, there are 4 possible ontic states, and the most one can ever know is 1 bit of information about which ontic state is the true one. So from that one principle, and holding the same principle for two toy bits, that the most you can know is 1/2 of the total information, and for 3, and so forth. The most you can know is 1/2. He was able to get back a lot of properties of quantum mechanics. So similarly here, I'd say if you can find one principle that's not strained, and the formalism seems to be telling you over and over, hey, look at me, like the idea that quantum states are incomplete descriptions, as much Joseph and I do agree on. It seems like the formalism is calling out to you. Why? Because all you do is you look at some little model of an incomplete description, and you see it's got formally 20 kinds of things that quantum mechanics does too. The Bohmian conception, I would say, says, I'm going to treat this like a classical field, whether it looks like one or not. And it happens to not. So, you can make it happen, but you got to so stretch the shoes that.
Yeah, I'm not arguing for both. It seems like a cop-out or a cheap solution, as Adam said. But it seems even worse to me to throw away, like even if you don't want to accept an idea of like I perfectly know reality and you perfectly know reality, and there's some transformation between them. Maybe we both know like some projective subspace of it, right? But it seems to me that it's it's not even clear to me what you think reality is, beyond that it's not this naive view that I've sort of held since I was, I don't know, like 8 months old, right? Like this is what I thought reality was then, this is what I think reality is now, and now you're saying, oh no, I have this better notion of reality, or this different notion of reality, but like what is that notion of reality that I should exchange my own notion for? If you're
my guess is that my point of view is much closer to the one that you had when you were 8 months old. It's just the reality is what's around you. Hey, Mom, she's there. You don't doubt it, do you? But it seems like, oh, we've gotten very sophisticated. Mom's not really there. She's a disturbance in a universal field of a very sophisticated variety. That's a hell of a story, all the way from that up to what you see. It's a story that's so complicated, no one's ever told it. I shouldn't say it, but let's think about the hard problem of the quantum to classical transition. Has anyone ever solved that problem to the T? To the T. Has anyone really solved that problem, taking quantum mechanics and rederiving full classical world from it? Would you say that it has been done? Or is there just a faith that it can be done? Okay, so should I go on with my own stuff, or what do the professors say? Okay.
So it's just kind of a
So are you saying you're taking a non-reductionist view of reality? So the fact that, for instance, my mother, which I recognize, you're surely not disputing that if I break down the matter, I find a bunch of protons and electrons and all these sorts of things, right?
It ain't really horrible things to people.
Well, okay, fine, my shoe or whatever. So you're saying that by virtue of all of these particles and forces being so combined in such a way that it somehow becomes more than just the combination of the particles? Like, I don't really...
I wouldn't say it that way.
So is a shoe made up of, for instance, a disturbance in a field?
I wouldn't say that.
So what's the difference? Yeah, what would you say?
Oh, it's right there in your language. You say, would you say that it is made of these things, and when I put them together, something new arises? No, I wouldn't say that.
Okay. Well, what would you say is a shoe?
I would say a shoe is something I put on my foot.
But there's a difference between objective reality and your perception. So I agree that in your mind you recognize a shoe as a certain object because you have a familiarity with it. But doesn't that could just be formed by, I mean, in that you're including, I know how to use the shoe, I know how to tie the laces. So this is your conception of a shoe. And that is more than a disturbance in the field, but from just an objective physical point of view.
The neutrinos zipping through your shoe don't share the same idea shoe as you. So what is the essence, like what is the shoe in this? What is really the shoe?
Well, there is a long, actually, I mean, there's no doubt I would have to go into it to adequately address it, but it's a tough one. You know, for instance, you know, you say, well, what are you really made of to someone? Aren't you partly made of gravitational field? You've been on the Earth all your life. If you take somebody away from that, are they the same person as their body starts decaying and the calcium starts leaving the bones? Why do I bring this up? It's because there's a completely different sort of mindset involved in the non-reductionist business. And I don't think I can do adequate justice on the fly. I can do justice to some questions, but that's, you're asking a really tough one. If you are curious, I'd recommend reading a couple of Nancy Cartwright's books. One called The Dappled World. Stop as soon as she starts talking about quantum mechanics. And another one is called How the Laws of Physics Lie. And stop when she starts talking about quantum mechanics. And these are attempts of talking about the world where you sort of leave nothing out, and it tries to answer your question. What is different here than saying, well, it's built of these things and new properties emerge? Instead, it's the other way around. But I'll just leave it at that. I don't think I can answer you well.
Let's thank Chris, and we'll see you next week.